All right, good morning. So today we are going to, today and Friday, we are going to go on a 2-lecture series about an idea called heaps. So what we have learned so far is this idea of binary search trees and how to do insertion and deletion into them. And the benefit of the binary search trees allows us to do a divide and conquer approach. And the drawback is that we have to use all of these pointers and balancing mechanisms to be able to prevent a worst case scenario. So we learned about AVL trees and we learned about this as well. So we've also learned about priority queues. So in your Creativity Challenge 5, you built a priority queue based upon a sorted doubly linked list. And what you learned is that a sorted doubly linked list, if you sort it from 1, 2, 3, 7, 12, that when we built our priority queue class, we had to account for the fact that the smallest number would be first. So if you sorted it the other way, then we could have a priority of the value be the highest. So a lot of what we want in terms of priority depends on what it is and what the task it is that we're doing. So for example, if for some reason I was asked to sort all the students by grades, right? And so I would say, all right, here's all the information, I'm going to sort it, and then I want to have some sort of way of coming up with a full list. So I would sort it into the priority queue and then pop them all off the queue. And the student with the highest grade would be the top, second highest student, and so on. So for each of these, we built them off of, so the previous one we built off of doubly linked list. And so for priority queues, one can just be sorted using an integer type here, move that. And then the type that you wrote is called a separate priority parameter. And what this has is you have some sort of value. So in this case, in the first test that you came up with, I had those standard strings, and then we had a priority, and then we put it in there and popped them off. It gave the words to cheer, cheerful Notre Dame, right? So that was based on the priority and the elements in the priority queue. And with the sorted doubly linked list, we learned that this takes big O of n time. So the question is, can we beat this? Can we beat big O of n in a way that ensures that the element is still, the way that ensures that the element that we want, in this case, the largest, can be accessed immediately. And so the way we're going to do this is what's known as a heap data structure. And so a heap data structure, we're trying to provide an efficient implementation for our priority queue. And we have and ignore that, this heap property is such that for what we're going to call a maximum heap, that any node, its children are both smaller anywhere in the tree. So this is a valid tree because we have 81, and then 81's two children are 27 and 33. We don't care what order those are, just as long as we know that those two are smaller than 81. Likewise, 27's children are 21 and 1, and 33, its child is 7. Now here's the interesting thing. That is also a valid max heap. Even though 29 is greater than 27, it doesn't matter because 33 is less than 81 and 29 is less than 33. So if we have it in that specific order, then our maximum heap is maintained. Later in the slides, I'm going to talk to you about this, how a heap is also known as a complete binary tree. And what this means is we're going to put the next element into the tree in a place where the 7th element should go. So it would go here, then the next one would go here, and so on. So this means this complete binary tree would be the smallest possible binary tree that we could have. So let me take you through an animation and show you how it is that this goes through. So let's say I wanted to put in 44. So the first step of 44 is I would put it at its logical location. So now we have a complete binary tree. The thing though is that 44 is greater than 33. So now we have violated our heap property. So now what we're going to do is we're going to do a process called heapify. We are going to move this element up. And so we see that 44 is greater than 33. So the easiest way to fix this is just to swap them. And now we see that 44 is less than 81. Therefore, we have a valid maximum heap. Does everybody see that? So I kind of went along with some of the memes. So from Star Wars, the Revenge of the Sith, where the first Obi-Wan says, "Anakin, I have the high ground." So that's what Max Heaps. This lecture is called "Anakin, I have the high ground." And then the next one, we're going to do Min Heaps, which is at the bottom. It's going to be Anakin saying, "You underestimated my power." So that's the name of Friday's lecture. But going into the Star Wars theme here, the thing about heaps is that we're not going to use pointers. We're going to use a dynamic array. And the reason why is that the inventor of the heaps, J.W.J. Williams, he's also named John Williams. So for those of you who are really into Star Wars, there's a lot of Star Wars themes going on here right now. When he was working with binary trees, and this is at the time when computers are very limited in memory, he thought that pointers were very cumbersome and unnecessary. And so it's like, well, is it possible we can get all the benefits of trees without having to do all of this sorting? I don't have to do all this sorting and maintain all these pointers. And so I have the quote here from Star Wars where it's JWJ, "He doesn't like you," and here are the students in the background, and here I have a pointer. "I don't like you either." So there's a lot of, okay, so and these jokes kill an intro to computing. I don't get what's going on here. Okay, so sorted dynamic array. What's actually going on here in the max heap is that it's corresponding in a dynamic array. And the way it works is that the parent here, its two children are here and here. 27's children are here and here. 44's children are here and here. So the way it works is that if I have a value, let's say that I have a value, we say this is 7, right? So 7 divided by 2 in an integer is equal to 3. So 3's parent, right? That's right, it's the third element here, right? So 7 divided by 3 is here. So if we did this with, and we'll see this in code, that when you have the 0 element, it will be I minus 2 minus 1 here. So 7 divided by So 7 divided by 3, or 7 divided by 2 gives you 3, minus 1 is 2, so therefore 44 has that. Likewise, if we pick here 1, it's going to be 5. 5 divided by 2 is 2, minus 1 is 1, and we see that 1's parent is 27. Oh, sorry. All right, so let's take a look at how this change would actually work in animation. So the way this will work is that here I have a currently existing heap. And then I put in 44 just like we did before. And it's going to be put at the location in the array that is the dynamic array's, the complete binary tree's logical location. Then I would check the parent. Are these two bigger? 44 is bigger than 33. So in this case, when I swap them, what's going to happen is that 44 and 33 will be swapped in the dynamic array. Now, before we continue, does anybody see a potential issue with this? Does anybody see any potential issues? Think back to AVL trees. What are some potential issues with the AVL trees? Yes. Right, so we have to make sure we have to heapify up, and then we also have to make sure that our left side, that doesn't cause any issues either. So now what I'm going to do is I'm going to insert a minimum and a maximum. So here, 0 would be first put in its logical location at the end of the array. And then I check the parent, in this case it's 21, and 0 stays put, right? And the reason why is it's a max heap, and 0 is less than 21. So now what I want to do is I'm put in 99. So initially 99 is put in that next location. So we still have our complete binary tree. And now 99 is greater than 21. So we're going to swap them in the array. Now 99 is greater than 27. So we're going to swap those in the array. And now 99 is greater than 81. So now 99 is now at the top of the heap. And you can see at the top of the heap, we have the logical representation on the left. So going back all the way to this different levels of abstraction, we have a logical representation on the left of the maximum binary heap and the dynamic array representation on the right. And so first, let me show you, okay, first, before I do that, does anybody have any questions before I continue? Yes. Correct, it's all going to be in the dynamic array. Now, let me check the chat. Okay, I don't see anything in the chat so far. Yes.
So when you insert an element, it's always going to go to the end of the dynamic array originally?
Yes. So yes, the question is, when you insert an element, it will initially go into the end of the dynamic array. So if I put in 56, 56 would go here as the left child of 1, right? And then 56 would come up here and swap. So these would swap. Now 56 is here in the dynamic array, and 1 is all the way at the bottom. And then 56 is less than 81, so now we have our heapification taken care of. All right, any other questions? All right, so what I want to do is go step by step into how I designed and tested the maximum heap. So in max heap 1.h, I have a templated class, and we see that I've included my dynamic array that we built together in lecture. And I have a private method. And so first, before I show you this trickle up method, I want to show you the constructor and everything there. So first I have the public constructor, and I call it heap array as what I'm constructing. And heap array is a dynamic array that we've templated to the same type. So I have this private, there it is. Didn't even have to move. So I have that private member heap array, and I'm in the member initialization list, I'm calling the constructor. And then I have a destructor that doesn't do anything. And then I have copy constructor. And the way the copy constructor works, and since we now know that this is built off of a dynamic array, that first I call the constructor for heap array based on the size of the dynamic array of the copy. So here I have copy.size, and that's a method that I've used to return the size of the dynamic array. And then I iterate through, so I have copy.heapArray.size, iter plus plus, and then I push back onto the array these elements. And so now I'm just bringing the copy of the dynamic array. And then for the assignment operator, I'm doing the same thing. I call the max heap by reference. For the assignment operator, I do that test if this does not equal the address of the right-hand side. So we make sure that we're not copying it to itself. And here, because we're using this versus the right-hand side, we want to use the this operator to push back, but we're doing the same thing. We're copying all of the elements from the dynamic array into the heap. And then I return this. Does everybody see that so far? So here I just have default constructor. Then I make the heap rule of 3 compliant, which we've just discussed. And then the next thing I do is I have a public push method, and then I have a private tickle up method. I'm going to show you more clearly in the code what's going on here. But to address a question that's come up a few times, why is it a good idea to separate public and private methods? So in a public method, all the user should do is put in an element, and then some sort of magic occurs that you have written, and then it does the work, right? The private method is where we start accessing the private members. We do a lot of the recursive work itself. So first, what I would like to do is I'm going to take you and show you this public push method, and then I'm going to scroll up and I'm going to show you a method that's called trickle up. And that trickle up method is the approach to putting that up the tree. So here I have this public push method. And in this public push method, first I push back the element onto the array, and then I'm going to trickle up, and I'm going to start at heap array.size -1. So what I have done is I've put an element at the end of the array, that's the location of the representation of the complete binary tree, and that last value will get the value that I've just inserted into the dynamic array. Does that make sense so far? Okay, so let me check the chat, see if there are any questions. Okay, so now we are at the private trickle up method. And what I'm doing is I'm passing the current heap location. And this is where understanding where the parents are in the dynamic array becomes beneficial. So if heap location is 0, then we're just going to return, because now we're at the root. No need to do this anymore. So now what I have is heap unsigned int parent, heap location -1 divided by 2. And that's going to give me the location of its parent. And now we're going to perform the trickle up. So here I have it commented that it could be implemented recursively. Here I'm also going to implement it. I'm going to implement this with a while loop, just to show you, kind of walk through and show you how it's actually working in the max heap. So what's going on here is I say while parent is greater than or equal to 0, and the heap array's parent is less than the heap array's location. So what's going on here is that in that scenario where I had 33 and 44, I would say 7 -1 is 6 divided by 2 is 3, and that gives me the location of the parent. And then I compare that to the actual heap location. The next thing I do is I perform a swap. So I have t temp is equal to the parent location, parent is now equal to the heap location, and heap location is equal to temp. And now what I do is I say, if parent does not equal 0, heap location, now I've updated that to the parent. So now I've moved it over, and now we're going up the tree. And then I say parent is equal to heap location minus 1 divided by 2. And if you notice, I have that comment there that dividing the 2 there as we move up gives us big O log n runtime. So now we're getting it, now we don't have to evaluate every single element in the heap. We just have this specific thing that we need to do. And then we just loop through, and that involves us heapifying all the elements to the top of the tree, to the top of the heap, excuse me. Does anybody have any questions about that code before I continue? Now, I have a program, test max heap 1, and what I'm going to do is I'm going to create 2 heaps. One is an integer heap and one is a character heap. And what this program will do is I'm going to push on, and then I'm going to call an overloaded operator. In fact, let me show you the operator that I have in test max heap 1. So this is all the way at the bottom, and all I'm doing is printing all the elements out in the dynamic array. So that allows me to show you the actual array representation of the heap at every single insertion stage. And here in test max heap 1, that's what push and print does. I call the heap by reference, and then I push the element onto the heap and print. And then I do the same thing with character. So let me run make test max heap 1. Let me make this bigger so it's visible to everybody too. It compiles and runs. So initially it's 33, then I have 33 and 21. And then here, what happens is I put in 81, and it goes, nah, I need to switch that. So it trickles it up, 81 and 33. And then we put in 27. So we put 27 here. And we see that 27 is now the second element, which means these elements got switched. Does everybody see how this is working? So far, so good. And then we have the same thing with the character heap. So now let's remove elements from the heap. So it's a heap, right? Our goal is to make this go to a priority queue. So the most valuable piece of information that we have in the max heap is the element at the top, which means that we have 99. So 99 is the element we want to get. The next crucial aspect of the maximum heap is that the element that will be at the top should be the largest element. So in this case, it makes a lot of sense. 81 is just there. But I want you to bear in mind that 44 and 81 switched around. That is still a valid binary heap. There's still a valid maximum heap, which means we can't just grab the element here. We have to go through a process of picking where the elements are in the dynamic array. So what we're going to do is we're just going to initially delete it. And then we have a couple situations here. If we just moved 81 up and didn't do anything else, let me go back through the animation so I'm clear. So it was 99. And then what's going to happen is if I just delete this, the next animation is going to show what the heap would be if we just left it alone. Did everybody understand that? So if I just took this out and I clicked what's next, that is what the logical representation of what's in the array looks like. So we have some issues, and they occur specifically here and here. 33 is now greater than 27. 21 is now greater than 1. So we have to account, and this is what you were just saying when you correctly answered, we have to account for scenarios when removing elements from the tree creates these kind of issues. So the question is, how do we know where to move it so we can maintain the complete tree? So here we're back to where we want to be. And now let's use what we remembered about binary search trees and AVL trees, and we're going to do the same concept with deletion. we are going to swap the element that's currently at the bottom, which is 21, and 99. So we're going to swap those, and now 21 is going to be at the front, and then we would delete the last element in the dynamic array. Does everybody see that? And so now what we need to do is we need to figure out a way to push 21 down to its correct location in the heap. The other crucial thing we need to bear in mind is we want this to be a complete binary tree at the end. So we have to be knowledgeable about how big the tree is and how that will correlate to which way we should go. So let's take a look at a binary binary heap, and figure out which way we'd have to go left and right in order to be able to get to any location. And you'll see a specific pattern here. So if I want to get to node 11, first I have to go right, then left, and then left. And we see that, correct? And so we see that every single element in the binary tree or in a binary heap has this same kind of pattern. And since it's a complete tree, we have to bear in mind these patterns. And these patterns also correspond, we can think of them in binary. So here's the previous slide. And now we switch it to ones and zeros. So I have 0, 0, 0. I have 1, 0, 1, 1, 1, 0, 0, 1, 0, 0. And the pattern is that I can mod it by 2. So 7, 7, 7, like so. And so now we can use this pattern to figure out which way we want to go, given the size of the binary heap, how much we want to, which direction we need to go in order to properly heapify it down. Does everybody understand that? So this allows us to say a pop method that calculates which way we want to go. So first thing I want to do, so let me show you in heap max 2. So first I'm going to, so in the public method pop, I apologize for this. Okay, here we go, we found it. The first part of the pop method is going to be what we do in the animation. So in the animation, I say, well, if the size is equal to 0, I can't pop anything and just return. So that's a level of protection there. The next thing I'm going to do is I'm going to say that heap array 0 is equal to heap array size minus 1. So the element that's currently at the bottom of the heap is now going to be put at the top of the heap, and that allows us to pop the element off of the top of the heap. So that was the scenario where we had 99 and we had 21 at the bottom. And so now we're using that same kind of policy that we used in binary search trees and AVL trees to move it up and then delete the element at the end, which is what we do here at this line. Array, heap array, dot erase, heap array dot size minus 1. So now we're removing the last element from the heap. So at this point, we have a complete binary tree, but the element at the top may not actually be able to meet the heap requirements. So the next thing we need to do is we're going to write a private method to test how far we need to heapify down. Does anybody have any questions on that before I show you how we're going to do this? And so the way I'm going to do this is we had a trickle up method to move it up. So let's come up with a trickle down method. And the trickle down method, what I do is I pass heap array size minus 1. So that is the last element. That's the location of the last element in the heap, in the dynamic array. And then I'm getting its parent. So now what I'd like to do is I'd like to show you the trickle down. Yes. Right, so when you erase this location, you're erasing it from the dynamic array. And so when I call dot size again, So if my heap array had 7 elements in it and I erase it, it's now going to have 6. So when I call it again, this is going to be 6. So that's where we take advantage of the dynamic arrays methodology. Sorry. Did that address your question? Yeah. Awesome. All right, let me check the chat before I continue. Okay, I don't see anything in the chat. Okay, so now I'm going to take you to the trickle down private member. So here's trickle down, and I have previous value and next value. And say if the next value is equal to 0, that means that we've reached the root and we just want to return. Otherwise, I need to determine what the next value is. And so the way I'm going to do this is I'm going to create a temporary value. And then what I'm doing is I'm going to say if previous value mod 2 is equal to 1. So now I'm using that pattern, right? It's either going to be 1 or 0. Now I'm going to say is temp val is equal to previous val divided by 2. And what I'm doing here is I'm actually creating a recursive trace where I have all of the possible changes that I need to make and follow the pattern. And at the end, what's going to happen is when I try trickling it down, what's going to result is that the element that's going to be at the end of the dynamic array is going to be in the right location that we've maintained the heap. And because we're dividing it by 2 every time, we still have this log of n property maintained. Does everybody see that? So here's what I do with that temp value. I recursively call the trickle down. And I take advantage of putting all the elements onto the instruction stack and all the calls by reference to set up. I start at the bottom and I follow that pattern all the way up to the top of the heap. So let me draw what I just did with my hands here. So I would follow the pattern all the way down. I'm sorry, I'd start it down, and then I would create a pattern all the way to the top of the heap. And what this allows me to do, once I've made all those recursive calls, is then I can start making decisions on what needs to be pushed down the tree. And the way that I do this is I say that if the next val is greater than the previous val, then I perform a swap. So by using the recursive properties that we learned about earlier this semester, and the importance of understanding what's going on in the instruction stack, we can actually make this a little simpler. Does everybody see that? So let me run test max heap 2. And in test max heap 2, it's the exact same code as test max heap 1. Except the only difference is now I'm including max heap 2.h, which is what I was just showing you. So for max, make here. And so now we have our pushing and our popping. So I'd like to show you something before we see the solutions here. So here what I want to do is to get to 14. Oh yeah, so you eliminate all these. Eliminate 10. Oh, I'm sorry, to get to value 14. So here, let me apologize. So to get to 14, I'd have to go right. And then what happens is I would say for 10, I made a smaller version of the tree, so I have to go to left, right. If I want to go to 9, I have to go to left, right, left. And so let me show you the animation going through this code. So first I would swap 99 and 21, then I'd remove it, and then we go to the private trickle down method. So previous value is 3, and next val is 7. So now I do temp val is equal to previous val divided by 2, so that's going to give us 1. And then I call the recursive call, so now it's 1 and 3. It's not equal to 0, so 1 divided by 2 is going to be 0. And then I make the recursive call again. And now I do temp val and previous val And that becomes here. And I did the same thing here. Does everybody see that? So now what I've done is when I get to this recursive call, if I hit 0, I just return. Does everybody see that? Now I'm back up, and I say a previous val, sorry, there we go. And what this allows me to do is allows me to say, I'm sorry, next val is equal to 0. My apologies, I was a little confused by my own animation. So next val is equal to 1, so we still keep going. I set this here, previous val is 0, 0 divided by 2 minus 1. And now I'm taking advantage of my knowledge of unsigned integers to do a little trick. And what's going on is that when I make this next call again, next val is equal to 1, and the previous val is equal to the unsigned integer. So here I get next val is equal to 0, which means that the current val would be -1 here, which means I now know that I've already reached the top of the tree, and then I can create my entire path. So then when I leave, I'm going to move up, and now I'm at 0 and 1 for previous and next val, right? So now I'm going to go on this recursive. So 0 and 1 is 21 and 81. And so in this case, 81 is greater than 21, right? So therefore, now I do a swap. And now we see that 81 and 21 are swapped. And now we're at 1 and 3. 0, 1, 2, 3. 21 and 27. 27 is greater than 21. And now I swap again. And then I'm at 3 and 7. 3 is 21 now, 4, 5, 6, and 7. And so now we see that we went through the entire pattern correctly based on the size of the remaining tree. So then we swap again. We check that. At this point, 21 is greater than 0, so we do not swap. And now we have heapified the tree. Did everybody see that? Question. What is the potential issue with this? Let me go to here, right? So now I'm at 21 and 27, right? So before it was 81 and 27, right? So if I'm following this pattern, I'm comparing these two because my goal is to get this down here, right? So what is a potential problem with just swapping 27 and 81? Yes. Exactly right. So the statement is, I'm back here. Let me go up one. Okay, so we're at 21 and 27. And previously was 81, right? So this could be 65, and that would have been a valid heap, right? So when I swap those values, 27 would now be above 65, and therefore we have violated our tree. So now we have a situation just like the AVL tree where we need to consider the other balance. Okay, so here I'm going through this. Let me just quickly go through the same thing. So now we pop everything off. And this scenario where I've circled is what you've just identified correctly as the problem with our tree. And see, it actually happens precisely at 27. 27 gets too high in the tree. And the thing is, you'll know this will work. We see that it's 27. So let me draw out the logic here. 27, 1, 7, 21, and 0. So now we have to account for the other side, and that's where the next change in the maximum heap will be. There's the animation showing what I just drew out. So let's walk through and see what happened, and now we're going to identify the opportunities based on what's done here. So we have 0. 0 is removed. And now what's going to happen is, in order for this to be the correct location, I'm sorry, in order for this to be the correct location, we need to get 1 here, right? So what's going to happen is we're going to swap these values. 27 is bigger than 7. And so what we need to do is we need to check the hierarchy. So forgive me for skipping this slide, but this is just what we described before. So let me go back. So here we have 7. We're going to then check 7 and 27, and then check 7 and 21 again. And at each place, what we need to do is we need to check and make sure that our swap did not inadvertently cause a problem. Otherwise, we'll have to perform a trickle up. So at each level, when the heap has 2 or more nodes, there are 2 cases we must consider. One where we have both values, and one where we have 1 value. And since we fill them in a specific order, we would not have a situation like we're not going to have null pointers because we're going to be using the dynamic array. And that can only occur when parent times 2 plus 2 exceeds the array length. And so for a double, the final should have the maximum of A, B, and C. And for a single, it should have the maximum of A and B. And so let me show you in Maxed Heap 3 how I modified the code in both trickle down and trickle up to be able to account for this to remedy our problem. So in Maxed Heap 3, here, I'll just show you trickle up. So we do the same thing here. We have that same location. And in trickle down, I had that swap, but then check it out. I have this if-else statement. And so what I'd like to do is walk you through this if-else statement. Okay, I apologize for the constant moving. There we go, got it. What I'd like to do is I'd like to walk through this code and show what's going on here in order to be able to demonstrate how we have adjusted this issue to be able to get a proper maximum heap every single time. So first I say check left for improper issues. So first I say if heap previous value is less than heap times previous value plus 1, so now I'm checking the left, then I do trickle down with those 2 values. So I've identified a problem and then I run a trickle down. And then I check down even further. Now I'm checking the children each side. And then likewise, I do this for the right. If 2 times previous val plus 2 is less than heap size, so this condition I showed in the slides. Let me go back to the slide really quick and I'll show you what I was alluding to here. Here what I have in red. What I'm doing is I'm making sure that we don't unintentionally exceed the array length that I'm trying to check right. Dr. Morrison at one point when he wrote his code got some seg faults and wanted to make sure that didn't happen to you. So there, I'm just checking to make sure that we don't unintentionally exceed our improper issues. And then on the inside, I use the same thing where I'm checking, in this case, 2 times previous plus 2, which in that case, if I'm currently at 3, that's 2 times 6 plus 8. And that gives me the specific right child. And so that makes sense. We have 0, 1, 2, 3, 4, 5, 6, 7, and 8. So 2 times the value plus 2 is going to give me the right child that I want to look for. So first I check to make sure that we actually have an element there. And then I want to check and trickle it down. All right, does everybody understand that? So let me take you through the new test. So now what we're going to do is we're going to fix the issue by recursively ensuring ordering. So I would pop off 33 from the tree, and this would swap 0 and 7. Then I remove the last element from the dynamic array. And so now I want to make sure that I go to this specific direction, right? Now I have previous value 1 and next value 4. And so now I create that exact trace. So here I got to previous value is -1 and value is equal to 0. That was the end of the recursive trace. So now we have 0 and 1, and that's 0 and 20, the value 0 and the value of 27. So we're going to see that those are swapped. And then here I have 1 and 4. That's 0 and 1. And now I have this, but now we see that we violated our property with a 1 being greater than 21. But that's okay. Now we've accounted for, we want to look left. And now we're running that code, heap array previous value is less than heap array of 2 times previous value plus 1. So this is 1. 2 times 1 is 2 plus 1 is 3. So this is 0, 1, 2, and 3. So 1 and 21 are now being compared. And since 1 is less than 21, now I want to trickle that down. And now I hit that recursive call. When I go up, it's now 1 and 3. I compare those and we swap them. And then we go through the entire recursive tree. And we now see that when I run make test max heap 3, that we go through the entire order. So let me run this for you, and I'm going to show you. So it runs. And notice, look at the very first number in each of these printouts. So first I pop off 99, and then the first element is 81. I pop off 81, the first element is 44. I pop off 44, the first element is 33, 27, 21, 7, 1, and 0. You all see the pattern there? We have now created a way to sort these elements. And this process of using a maximum heap to provide a sort in this way, by pushing them all onto the stack, onto the heap, and then popping them off is what's known as heap sort. And we see that this is the same thing. We have Z, Y, X, M, C, B, A. So I have it from maximum to minimum. So it is a maximum heap sort. So there we go. We have all the stuff there. So just what I just said, there it is. And so what I'm going to do in this function, in this code, max heap sort.cpp. So let me show you the actual .cpp file. First, I want to go down to main and show you the general idea of what we're doing. So first, what I've done is I have created a maximum heap and I've created a stack. And so I'm going to push and print 9 elements. It's going to be the same elements as before. And then I've created a new function, pop and sort. And instead of just popping it and printing it out, I'm going to pop it, but I'm also going to call the stack by reference. And I'm putting all the elements onto the stack. And since it's last in, first out, what I'm doing is I'm reversing the order from smallest to largest. And then what I'm doing is I'm popping all those elements off. So we see that? And then I'm doing this, going to do the same thing with the characters that I've done before. So let me run make max heap sort. And now I have the sorted result as well as the ordering of the heap at every single stage that's printed out. So if you want to play around with this when you're studying for the exam, this is a great way to do it. Just modify the code that I have there and say, all right, what I'm going to do is I'm going to put in these values. What's my sort going to be? I'm going to put in these other values. What's my sort going to be? So it's going to be a string. Should I do a double? All these different things, because we've used genericity and we've used our previous classes where we've emphasized this idea of modularity and genericity, we can now do a heap sort on anything that has a comparison. So the thought question that I have that I want to take into Friday's lecture is, well, what happens if I want to actually preserve that minimum ordering? We can't preserve it because we have to pop everything off the stack, right? So what we're going to do on Friday is we're going to do a minimum sort. We're going to use inheritance and polymorphism to build up of our maximum heap, and we're going to build a min heap. And then from there, what I'm going to do is I'm going to show you how we can use the minimum heap to accomplish the priority queue that you all did in Creativity Challenge 5. And then we're going to conclude that lecture by comparing and contrasting the pros and cons of implementing in both of those ways. Does anybody have any questions before I dismiss? Let me check the chat. All right, on that note, it is 11:15 and you're all free to go. I will send out the assignments for the pre-internships today and then arrange the introductions by email with your mentors and TA.